Okay, hello everyone, and thank you for joining us on the Goose webinar. And we're going to be hearing from Neville Smith and Bob Weller around 20 plus years of looking at the sustained ocean observing system for climate. This is a new approach. We're talking to you live from the Ocean Observations Panel for Climate Meeting, the Goose Physics and Climate Panel in Woods Hole, where we're meeting this week. So firstly, the usual format is we will be online for about an hour. The presentation will take more or less 30 minutes, and then there will be an opportunity for question. Of course, we have a room full of people here this time, so we'll have some questions from the room as well as questions online. So feel free to type in your questions online, and we can then read them out from the room to make things easier. Okay, so just to announce our speakers. So we have here Neville Smith. He was the first ever chair of the Ocean Observations Panel for Climate. He joined in 1996. I would say he's known as a real change maker in our community and through many projects and activities. He was formerly Deputy Director of the Bureau of Meteorology in Australia and now co-chairs the Tropical Observing System 2020 project. And we also have Bob Weller, another long-time member of OWPC, and he's a senior scientist at Woods Hole and is a pioneer in developing tools and technologies to measure the upper ocean over a long career. So I will hand over to Neville Smith to kick off this discussion. I hope you enjoy it.
All right, thanks, Katie, and hello, everyone. You're not going to hear for very long from me just now. I'm going to pass across to Bob Weller. We could have, in fact, included a good number of other people as co-authors of this. Mike McFadden, who has been around in this business probably even longer than I have, is also in the room here, and I hope Mike will be able to say a few words at the end. So the plan here is that after this very brief introduction, I'll get Bob to speak and show a few slides. Then I'll come back, and in my part of the talk, I'll go through a bit of a potted history of how we've got to the point we are at today, and then perhaps just do a little bit of looking into the future. So without further ado, I'll pass it to Bob, and I'll see you again in about 15 minutes.
Great. Great. Thanks, Neville. Yeah, we decided to tag team. We have pretty different approaches. And how do I advance, Katie?
Question. They're down the bottom here. I think here.
Okay, great. Super. So I go to sea and I do moorings and things, and so I thought it'd be a good perspective. I wanted to get across the notion that, you know, we really have made progress. And so I'm starting out by paraphrasing a Robert Frost poem, and whose observing system I think I know. The oceans are lovely, dark, and deep, and we have requirements, Neville's requirements to meet. And it feels like we have miles to sail before we sleep, So it feels like there's lots to do, but I want to point out that we've made some progress. And I want to point out, too, that the community is really pretty good at responding to some of the technical challenges. So won't belabor the requirements. The requirements are there for different types of moorings and time series and to measure air sea fluxes, which is what I do. So that's what I'm going to talk about. And as Katie alluded to, we've been at this for a while. So actually in 1993, Peter Taylor from the UK and I actually wrote a background report for the predecessor panel, OOSDP, on researching air sea fluxes in the fields, and we came up with a notional strategy on how to sample the ocean. And we got some very early tables of requirements, and in 1993 we thought we could go forward. And we kept working at this strategy, and by 1999 we had formalized it a bit, with the notion being that there should be some time series moorings we'd call flux reference sites, but there also should be volunteer observing ships with upgraded MET sensors. and that these in situ resources might be rather sparse, but they would work with remote sensing and modeling to accomplish the task. So that's the sort of thing we started moving forward on. I'll point out that it's not a new idea or a novel idea. Columbus Island was the second director of the Woods Hole Oceanographic Institution, and that's a quote from him saying, "The key, I think, lies in the best marriage of these two subjects, oceanography and meteorology. After all, it's one large heat engine." And basically, he's advocating an approach of doing moorings, surface moorings, that can measure both the surface meteorology, the meteorology part, and the oceanography part. So that's a technology that we thought was applicable. And we've pushed it forward, and the graphics has been killed by the translation from a Mac to a PC, so that's too bad. But my point here is that this is sort of the present state of a mooring. It's a mooring we maintain off the coast of Chile with NOAA support, and have done so. And you notice we've managed to load it up with about between 50 and 60 instruments in the water column. So we're doing these with pretty heavy payloads now. It's not to say that this was an easy thing to accomplish, and that's part of my talk, is that we're making progress. So on the left, a picture from the 1960s of an early Woods Hole Oceanographic Institution mooring recovery. Not going real well. That's what we call a wuzzle in terms of mooring technology. Now, on the other hand, I'd point out that on the right is one of my recent cruises off Chile, and if you look closely, it's a new challenge we're dealing with. We probably have some tens of kilometers of monofilament line from longline fishing activity entwined in the mooring. So it's a challenge, and it was always a challenge. And point out that when I started in the game in the 70s, a good day for a surface mooring was if we did a 30-day deployment in the summer. So, Jason 1972 in the Rockall Trough, the Joint Air-Sea Interaction Experiment, and then Jason 78, a good day for a surface mooring was a 30, 40, 50, 60-day deployment. In the MILE, or the Mixed Layer Dynamics Experiment in the Gulf of Alaska in 76, I think there was a 45-day deployment. So, this was a challenging thing to do, and there were some things that we had to work hard at. And Mel Briscoe was one of the pioneers of it, and he pushed forward in the North Atlantic, in the sort of Bermuda High area, trying to do a full 2-year deployment called LOTUS, or the Long-Term Upper Ocean Study. And this is some of the early surface buoy work we were doing. And one of the things we learned, and we learned it the hard way in 1989 when we put a surface mooring south of Iceland, is that mooring broke after a few months and it failed. And we learned that moorings are dynamic systems, and they could be forced by the surface waves and swell, and you got cyclic fatigue failures. If you took any of your mechanical engineering classes in college, you know that the failure curves march out really rather quickly at millions of cycles of flexural fatigue. And if you think of about a year deployment with surface waves every 7 or 15 seconds, you're getting millions and millions of flexing. But we overcame that, and we learned how to design moorings for deployment in really rough areas. And so that was technical progress. But now in LOTUS, we sort of, we ran into another obstacle. On the left, there's a little picture from Andy Bunker, one of the early hand-drawn maps of the net air-sea heat flux in the North Atlantic Ocean. It's based on ship data. And basically what Andy's contouring there are, all the contours are within about plus and minus 100 watts per square meter, with the exception of the Gulf Stream has a higher heat loss during the winter. But the point being that, if you looked in the Atlantic and you looked where the LOTUS experiment was being done, probably the annual mean net heat flux was about 60 to 80 watts per square meter. So as I came to Woods Hole and I worked as a postdoc for Mel, one of the things I was doing was I did an error propagation of the measurement uncertainty in the sensors through the bulk formula that we do fluxes. And in 1982, I figured out that the error in our net heat flux estimate was 205 watts per square meter. So against a measured mean that should have been 60, that was pretty discouraging. And even in those 2 years, as we tried to improve things, we didn't improve much. We got to about 100 watt per square meter. But, then things came along in the community, like the World Ocean Circulation Experiment and the Tropical Ocean Global Atmosphere Experiment. And the agencies were stepping up and putting some investment in technology. And we actually developed a new set of meteorological sensor technology called ASIMET. And these are just a picture of the different sensor modules that we started fielding And basically, if you look on the left now, on the very left is Andy Bunker's estimate of his uncertainty of about 100 watts per square meter. The next 2 points are very discouraging points of 200 and 100 watts per square meter for the Lotus buoys. But if you look to the right with time as we move into the Clivar era and beyond, we've really driven down the observational uncertainty in the net air sea heat flux with the sort of buoy that is on the right. So we have a capability now of doing something that we want to do to meet some of those requirements. And if you look at about a monthly average in the net air sea heat flux, we're good to about 8 watt per square meter. So we think things have improved, and I just want to show some other technology improvements with the mooring sort of systems and the new MET systems. We moved on to do some quite challenging areas. We did a deployment off Eastern Canada in the winter. We went to the Arabian Sea for a year, going through the monsoons. And this was the sort of data we were finding. If you look at the bottom plot, those are monthly means of QNet, so the net air sea heat flux. And the buoy is the black line, NCEP data. The National Centers for Environmental Prediction is the red line. The ECMWF data is the blue line. And the Southampton Oceanography Center climatology then is the dashed blue line. And I just want to point out things like, compared to the buoy, something like the NCEP heat flux in the summer monsoon had the wrong sign. And we're looking at errors in the models of up to 100 watts per square meter. So we thought, these NC2 buoys do pretty well, and it's an interesting contribution. And the counterpoint to that sometimes from the modelers was, well, that's just one point. The model's probably pretty good everywhere else in the world. You just picked a challenging point. So it took a few more years, and you won't be able to read this in detail, but just look, for example, that between the blue line, which is ECMWF, and the black line, which is the buoy, that in very different places from the Western Tropical Pacific and TOGA core in the bottom, up through the Eastern Tropical Pacific to the Central Atlantic, to other areas like the Arabian Sea and off Chile, these models have pretty significant errors. So we're making some progress here. So now this is the system starting to say, okay, we can do this. We can do this technically. So let's take a map of the world. And we're not going to be able to afford many buoys. So let's go forward and let's pick some characteristic sites. So we'll drop some sites down, the green diamonds. And if you want some spatial information, why don't we follow up on work that Peter Taylor did on the VOS, and let's upgrade instrumentation on VOS, and we'll get some spatial sections, and we'll start building air sea fluxes. And then, one of the things we realized was that might be good for the broad scale sampling, but there's other things going on, and something like the Gulf Stream has rather very small spatial scales. It has very sharp SST gradients, as you can see on the right. And Peter Taylor and his colleagues at Southampton were working on the climatology, and they were struggling with the notion of, do you take your QNet across the globe, and do you do the spatial average and force it to be 0 or to some small number? And when they did the spatial average of the climatology, it wasn't that close to 0. And they thought, well, we have to subtract a mean to offset that bias. But there's another way to view that. And another way to view that is that a gridded product on a broad grid may miss the very intense, very high amplitude signals. So we actually did a deployment in the Gulf Stream. And this is the time series with some averaging, with 5-day averaging at the top, running to the bottom. And this is the QNet. And I just want to point out that the highest 1 hour average QNet was 1407 watt per square meter loss. So that's a greater heat loss than the solar constant at the top of the atmosphere. So, I think it's a fair thing that we had to reconsider that if I had a very small area with a huge heat loss and the gridded product didn't capture it right, it's going to be a problem in that gridded product. So the second thing we said is, hey, we got to go out and we got to add. Oh, that graphic got clobbered. Well, that was from Lisa and you, and it was another perspective. It was the Indian Ocean panel where they did an analysis of the areas where the standard deviation between model products for fluxes was very large. And it led to a basis for making air sea flux reference sites maps in the Indian Ocean. So apologies for the graphics. It had seemed to work in the test. So going forward through the 70s, technology, through the 90s, moving into the 2000s, we have a plan. Let's go after characteristic sites, critical sites. Let's do fluxes better than 10 watts per square meter to do ocean physics. To address climate, we really want to get better at about 2 watts per square meter. And we have to work with somebody else to take the sparse in situ to make gridded products. So from Ocean OBS 99 in San Rafael going forward, the community came together and we started developing a global plan. And it matured to a plan like this, where these would be the notional air-sea flux reference sites. So these are surface moorings that we would maintain for a long time. And working with someone like Lisan Yu, we would identify biases and things. And this is just a month, December 2014 data from the northern Bay of Bengal, where we recently did a deployment. And again, we're comparing against the ECMWF and NCEP. And if you look on the bottom left, the wind stress curve, you can see that some models are getting pretty good, the black and the red lines. So the buoy and ECMWF agree pretty well on the wind stress during the winter monsoon. But NCEP, the light blue, is not so good. And if you look on the right, which are the 4 components of the heat fluxes, you're seeing some large errors of up to 100 watts per square meter. So there's still a place for these NCPC2 buoys to find out the biases and errors in products from remote sensing and models. So going forward, we use something like Lisan Yu's technology, and we put things together. Another point I wanted to make as I wrap up is, since we've been doing this, we now have some pretty long time series. And so off on the left, I've taken about 15 years of data from the Stratus region off Chile. The blue is the buoy, and that's SST. And all those other lines are the SSTs from the CMIP5 models. I just want to point out that it's really interesting that most of the models are all produce an SST warmer than the buoy. And I want to point out that the size of the bias in some of the models is as large as 4 to 5 degrees C. So these climate models, I mean, we can do things like test the realism of climate models. And then down on the right, we're using that buoy data at hourly time resolution. And I've picked just 2 of the models looking at daily products. And I'm just asking myself, well, what are they capturing? And off Chile, we can see the cooling related to La Nina. Well, the models don't see the cooling very well. So I just want to point out that the in situ resources are still key if we want to go and look at, like the CMIP5 models. Are they realistic in terms of climate? And you can compare them to long time series. Other things that we're doing, since we have the accurate sensors on the right, again, the same place off Chile, is I took the first 10 years of data, and on the left small graph, that's the annual mean net heat flux, and the buoy is the blue. And again, the European model's the red, and the NCEP model's the green. And on the right is the net heat flux. And what we saw over that decade is part of what seems to be part of the PDO modulation is the trade winds were steadily increasing and the heat fluxes were steadily changing. And I just comment on, look at the difference between the European model and the NCEP model in terms of how they agree with the buoy. So going forward, we can do these in situ things. So I think it's just an example. Argo floats, other parts of the technology observing system have matured. We have pretty good capability. We can't get away with not going to sea. We have to go to sea. Maintaining the quality of these sites, it's essential to go to sea. I just want to show you an example of a reason. So one of the things we try to do is accurate incoming shortwave radiation. The picture, it's a little hard to see, but those are 2 shortwave radiometers. In the center of the radiometers, there's a small black disc. It's painted with optical black paint. Beneath the disc is a thermopile network. When the sun shines on the optical black paint, it heats it. You get a voltage out of the thermopile. That voltage can be turned into watts per square meter. What I want to point out is, after several years of deployment, the one on the left, the optical black paint is about the color of cigarette ash gray. A new one on the right is nice and dark. And if you dig through the technical literature, I found this graph in the lower right buried in the gray literature. And there was a statement in there that these radiometers, because the optical black paint loses organic hydrocarbons, the solvents with time, they drift about 5 to 6% over 5 years. Well, it's something that we didn't know, and we had to work with Chris Farrell and his lab from Boulder and have a reference standard. Every time we went out and churned a buoy around, we'd have fresh radiometers from Chris's group, and we would check the drift and try to correct for the drift. So these are lessons learned. We got to keep doing these comparisons. As a community, we're trying to get even more aggressive, and the different people, I mean, China, Australia, and other countries are pushing to higher latitudes. So we're really pushing hard. This is the Australian mooring south of Tasmania. So we're trying to fill in all the holes. We're building more capable buoys. The buoys are carrying direct covariance flux systems, so we're not always relying on the bulk formula methods, which might be suspect in high winds and high sea states. These buoys that we're developing are more capable now, and we can carry new sensors. I think going forward, we have to work with other networks in the observing system, be more integrative across the blue water and the coast, work with the land-based radiation folks, the baseline surface radiation network, and we should work with other communities. We're already equipping some of the reference sites with deep ocean temperature sensors to answer the call of DEUCE, or the Deep Ocean Observing System. I think we should add biological and biochemical sensors. If we're going to go there and maintain these sites, we might as well make the most use out of them. And so indeed, on that idea, inside ocean sites, the time series planning group of observing, we were looking at this Longhurst figure in the biological provinces and trying to figure out how do we add things. And we're actually starting to do that with the community. This is a deployment of a buoy with an aerosol sampler. So you could look at things like micronutrient fertilization or DMS production. A young scientist here at Woods Hole Oceanographics, Sam Laney, fielded this buoy off of Hawaii, or added to one of our buoys, added hyperspectral irradiance sensors, and was doing phytoplankton biomass measurements from the buoy. So, we have these capabilities, and we're getting even better with these capabilities. And here's some severe weather environments and the new types of buoys. But there are issues and challenges, and this is where I'm going to hand off to Neville soon. I mean, what I want to say is, in many of our observing networks, we have an innovative, community. We have good people. We're pushing the envelope on the technology. We have pretty good success. But maintaining these arrays, requiring many ship days, is a challenge. I think we still have some challenges of working with the modeling communities, feeding them data in real time, or withholding the data as an independent comparison. So, the technology's good. We're on a good trajectory technological-wise. I would point out we're not going to plateau. I mean, we will always push the envelope on technology. We will add new sensors. So we shouldn't plan for trying to maintain a static network. It's always going to evolve. But this same strength that we had in many diverse small research groups and labs, I think, Neville, it might be a weakness in the sense that we're maybe not coherent in arguing for the operational support to keep it going. So I think those are the challenges I see. So there's a plus side. I think we're doing well, and I think we're capable. The negative side is, how do we keep maintaining this?
So thanks, Bob, and I think all those points resonate. So we've just had a deep dive on one particular area of the work of the WOPC. This is going to be slightly different because I'm now going to go to a more general look, if I can get the slides to move. And then go back one. So I'm going to start and talk very generally here, and my reference frame is actually going to be the WOPC, going from its first meeting up to the current meeting, number 20, and then I'm going to go forward and finish with WOPC 40 in about 20 years' time. So that'll be the last slide. So the potted history, and this is leading up to when we first started systematically thinking of the observing system. We were actually one of in oceanography, the foundations were laid down over 150 years ago when people started to take systematic observations in the Atlantic, and that then extended through to the Pacific and the other oceans. In an intergovernmental sense, it's about 55 years now since we started to set up an intergovernmental framework, first the World Meteorological Organization and then IOC. And there are a number of key things that were put in place very early on. The International Oceanographic Data and Information Exchange System was one of the earlier decisions of the IOC, but then it took us another 40 years to get to a point where we actually agreed in IOC on a data exchange policy. The Tsunami Warning Pacific was established in 1965, but it wasn't until we had the disasters in the last 10 to 15 years, for another 40 years, before it became a global and systematic system. And there are a number of other milestones in there which are relevant to the establishment of the OWPC and a systematic approach to the observing system. Two slides just to show you, where we were. Perhaps in this case, it's nearly 50 years ago. If you took 6 months of beta, and this is from the real-time system as distinct from the delayed mode system, this is what you would have seen in about 1970, the very early days of the Ships of Opportunity program. And you can see there were, a reasonable amount of data over 6 months in some parts of the North Atlantic and the North Pacific. Go to the Southern Hemisphere and there's barely an observation. Cast forward until the end of TOGA, the Tropical Ocean Global Atmosphere Experiment in 1995. And that experiment had certainly led to a great expansion of the lines in the tropical regions, but we still had lots of gaps in the high latitudes, particularly in the Southern Hemisphere. So now I'm going to get to the observing system and the mechanisms we've used to coordinate all of our considerations. The first of these was something that was called the Ocean Observing System Development Panel, which was created, well, it was formally created in 1989, but met for the first time in 1990 to 1994. And it was charged just generally with the design of an ocean observing system for climate. And I put in red, 4 of the people that are still hanging around here today are working on observing systems. Ray Schmidt, who's sitting in the room here with us, Mike McFadden, Bob, and myself. I also added a photo for those of you who want to reminisce of Art Alexio, who was supporting the Secretariat doing Katie Hill's job way back in the late 80s and the early 90s. I went down to see him last year, and whilst his health is not as strong as it was back then, he still keenly follows our work. The other chap is a guy called Bill Erb, who I'll see next week, in fact. The Ocean Observing System panel had a fairly broad charge. It was, when it produced the plan, it was published in about 1995. It was very aspirational. Bob Weller has already referred to some of the white papers. You might call them white tomes, because we had 10 of these publications before we published the report itself. They started off with Lilian Merlevat's, who was then, I think, was about 15 pages. Mine was 95, and then Peter Taylor and Bob Weller, of course, had to beat that. But they were they were fundamental in the way we did our research and the way we moved forward to the design. It was an aspirational plan. We thought we were out there and perhaps pushing the boundaries. But in the end, despite all the wisdom that sat around those tables over those 5 years, we did not foresee, well, at least not in detail, things like the Joint Technical Commission. We did not foresee Argo. We did not foresee G'day, the sea surface temperature projects, or indeed, in detail, the ocean sites that Bob has just described. Some of the other things, I think, were covered much. We in fact covered them better. One of the things I included, and this is more props for the audience that's in the room here than those listening from afar, is I've listed the characteristics of the observing system that plan was seeking. And it was where we laid out some of the characteristics of what a sustained observing system should look like. Long term, and this goes to the point that if we're going to maintain this and invest in this system, we really aren't doing it for a short sprint for 3 years. This has got to have timescales of decade or decades to really get the return on the investment. Systematic, this isn't done in an ad hoc manner. It must be done in a systematic way. It must be relevant, of course, to the climate system. We must continually subject the system to review, which was the topic the people in this room were discussing about a half an hour ago. It must, of course, be cost effective. When you're maintaining things for the long term, you really have to eke out every 1 and 2% of efficiency and effectiveness in order to make sure that you're getting a good bang for your buck. And of course, it has to be routine. This has to be something that you can maintain without, a large, complex effort. Again, for those of you who are watching from afar, this figure might not mean anything to you, but we've had lots of discussions in this room about feasibility and impact, and it's something now that we've embedded in the architecture of the Global Ocean Observing System. So the first diagram that we ever drew appeared in our report in 1994-95, and this was the one for SST. I'd love to say that we invented them. We didn't. They were invented, in fact, by the Coastal Panel, and we just borrowed them and made them a little bit more effective and a little bit better. As Mike McFadden would remember, we would have long debates about every one of these, and I think we published 12 of them for each of the different perspectives of the observing system. Then we go to the first meeting of this panel. This is the OWPC meeting number 1. I've included the agenda just to give people a frame of reference. And again, I apologise for those who aren't in this room and can see the agenda we've had for this meeting. And again, it just gives you a sense of the sorts of things that we were discussing there. Otis Brown at that time, who has been in this meeting for the first 3 days, was in fact the chair of what is now the Goose Scientific Steering Committee. And he hosted the first meeting down in Erasmus in Miami. We did a lot of discussion of terms of reference, and like all good groups, the first thing we did is try to change them. What we managed to succeed in doing is changing observations to observing in the WOPC, but we didn't get very far with most of the rest of it. We, of course, discussed the OOSDP report and its outcomes, user needs and products of the observing system, and then later on in the agenda, moved to very specific implementation issues. A lot of focus at that time was around the Ship of Opportunity program and its implementation. And because we were sitting down with Otis, we spent a lot of time at this meeting talking about sea surface temperature. We also talked about the space plan and how that was going to impact our observing system. We talked about a strategic plan for OWPC. Where have you seen those lines before? You'll still see them getting written into agendas. And in this meeting, again, we've had another discussion about a strategic plan for the climate components of the observing system. The process is similar, I would argue, but the basis and the backbone has evolved considerably. What we were looking at as an observing system in 1994 is hardly recognisable against the sophisticated, complex and integrated system that we have today. At the second meeting, and I'm just going to go through each meeting to give you a sense of some of the big things that were coming out of those meetings. So in the second meeting, which was held in Grasse in France in 1997, this was a meeting that we formally launched the Global Ocean Data Assimilation Experiment as a project of the WOPC. Michel Lefebvre, who was a member early on and was involved in, as many people know, in the TOPEX Poseidon launch, and was a great advocate for space and in situ, provided this little cartoon on the left, which I've used now for about 25 years. And the intention was to show that we needed theory, we needed observations, we needed a bit of luck, and we needed a lot of things in order to make that experiment in ocean forecasting work. The little view graph, and a lot of the young people won't even know what they are, up on the top right is one, and many people will recognise those initials, Eric J. Lindstrom. And Eric, of course, in his own way, just wrote down what he thought this experiment was going to be about. And pretty much that's how it turned out to be. It's only when you get down to the bottom of the assimilation fields that we start to see that there was a little bit of difference. Acoustic tomography really never did become one of the key inputs. And Lagrangian velocity, or any velocity at all, is still something that's not routinely assimilated in any model. But the top three, sea surface temperature, sea level, and temperature and salinity profiles, are really a core to what G'day is all about. The idea, and I list some of the things that were in the back of our mind. I mentioned a couple of names here. Christian Le Prevost, who unfortunately passed away, it's over 15 years ago now, was really the champion inside the panel at that time. And he spent a lot of time with me and others in making sure that this experiment was going to be a success. A lot of his enthusiasm was based around a group of people in France who met for the first time in 1996 for what we now know as the Machiavellian project. And it's lovely to look back at the photo of that group of people, a bunch of young scientists, probably their average age was between 25 and 30. And that enthusiasm, some of them still are 25 and 30. They haven't really aged at all. And they're still as enthusiastic as they were back over 20 years ago. We remained a little bit aloof from the intergovernmental systems. By that stage, I at least had about 7 years of experience of the intergovernmental systems, and I knew when to step away and only put a loose cord between that system and what we wanted to do. And it's a model that, in fact, has worked very, very well. It was focused, finite, and with an end. G'day itself finished in pretty much on schedule, maybe 6 to 12 months late in 2008. And its legacy we now see in G'day Ocean View and in an expert team in the JCOM framework. Going forward a year, and it was in fact the year that we launched the Argo initiative. I had to walk up and ask Ray Schmidt. We had two ideas on the table, one from Dean Rimmick, which was Argo. It was Argo, an acronym at that stage, and another one from Ray, which was Gossamer. And I had a look, Ray, and I cannot find your notes from that first meeting. I'll keep on looking. In some sense, we ended up following the ideas that Dean Rimmick had laid out, and these were the schematics from that meeting in July in Jamstec in Tokyo. But Ray's ideas, I went back and checked some of my notes, are really now starting to get picked up, and if you like, the second phase of the Argo program. The point I'd like to make out of this, and Argo has been just a magnificent success. Often you can put these things down to the people involved, and there's been great people involved right from the get-go in July 98 when we had, if you like, the launch meeting. It takes a long time. It takes a long time to get the technology ready to be deployed. It takes an equally long time to go from that to a fully deployed system. If I'd put up the TOW implementation for TOGA, it was a little bit shorter because Stan and Mike and others were, they worked much faster. TOGA always worked much faster than the WOCE folks. But it's still something that takes time to implement. And as David Legler has just pointed out about half an hour ago, no sooner do you think that you're there, then you have to start considering its sustainability and how it's going to endure for the years ahead. Going forward one more year, and this was a big year. Probably the biggest of the things that were being done at that time was Ocean OBS 99. And it was actually a project that we joined up with Cliver, something called the Upper Ocean Panel that Chet Kablinski was chairing at that time. It was also the year, and apologies, David, you were right, it was 99, not 98, when JCOM was agreed. The WOPC wasn't directly involved in that. It was indirectly involved through myself and a few other people. But it was certainly a big decision of the intergovernmental system to agree to its creation from the IGOS and Commission for Marine Meteorology. And I believe Peter Dexter, who is online in Australia and watching, is now writing a little bit of a history of this, and he played a pivotal role in making sure that got through all of the different complexities that were facing us at that time. The Ocean OBS 99 represented many things. It was a meeting of about 442 people from memory. We sort of lost count at various stages, but it was more like a workshop than a conference. It rained and rained and rained for 3.5 days, as everyone will remember. But it was wonderful because that meant that Chet and I could keep everyone in that conference room working on projects, working on plans without, any break at all. Chet had brought his golf clubs and he was really eager to get out there on the golf course, but he couldn't do it until we finished the meeting. It represented a paradigm shift from what we call then proprietary science to public good observing systems. Everyone agreed at that meeting that we had to change the way we behaved and follow the lead of the sea level observing system, of TAO, and start to release the data, if not in real time, as close as we possibly could. Those 450 people discussed all of the aspects of the observing system and made decisions on what was going to go forward. It laid the groundwork. Gary Myers was the lead author on a paper for the Indian Ocean Observing System. Steve Rintoul was the lead author of a paper on the Southern Ocean Observing System. And eventually those two are now gone forward into new forms. Decisions were made in the future. The endorsement of Argo was fairly simple, but we had a very, very energetic debate around ocean tomography. I can still remember walking up the corridor late one night and two people who I won't name followed me up there, one on both ears, telling me, this how great this was and it was going to change the world. In the end, there's still a place for ocean tomography, as we've discussed here today. But at that meeting, we just could not find a way to take it forward into a sustained observing system. Real targets were set, and the community that's joined since then will be accustomed to seeing figures like this. This one is actually from 2012, where people, particularly in the NOAA office and David Legler's predecessor, Mike Johnson, just followed routinely the progress in reaching those goals. And I don't think if you'd asked anyone in 1999 whether we were going to exceed them, not many people would have bet that we would exceed the surface drifter targets. We would eventually exceed the Argo targets and so on and so forth. So it was a great success, and it was great that people had the wisdom to start following that progress and really working hard. In fact, these diagrams do the observing system a disservice. Success was being counted, for example, in the number of Argo floats, yet the Argo capability that eventuated was many times more capable than what we started off with. WOPC 5, this was held in Bergen, was it? I forget. No, it was held in Kiel in 2000. And this was the time, in fact, in 2000, we held the meeting in November, which was the launch, in effect, of the Indian Ocean Observing System, the Sustained Observations for Climate of the Indian Ocean, another acronym to write down on your sheets. It was built on the Ocean Obs paper that Gary Myers drafted, and it laid the foundations for a lot of the work, and Mike McFadden introduced it here at this meeting. And again, when you look at where they are today compared to where we were thinking they would get to in years 2000, I think it's exceeded those expectations and exceeded them by a fair margin. It was also the year that the Global High Resolution Sea Surface Temperature Pilot Project was launched. This was perhaps the surprise, but it was also a very satisfying initiative. Ian Robertson from Southampton really was the architect of the idea, even though he didn't know it at the time, when he showed me this figure after a meeting he'd been to in Dalhousie, or a lecture he'd given in Dalhousie in the year 2000. And we've been wrestling with, why are we struggling with the sea surface temperature products, finding holes in the Bay of Bengal and a number of other areas where there are clouds, when we know we've got microwave sensors that can actually see through them? Why were we having trouble combining AVHRR and ATSR data? Why were we having trouble merging in situ data and satellite data? And based on this diagram, I just talked with Ian and said, well, why don't we put them all into a single system and do analyses that draw on every one of these capabilities? And that's eventually what the GRIS project did. We were very lucky, as we were with all of these projects, to have an eager young person willing to lead it. In this case, it was Craig Doland. But this experiment, in fact, probably turned into one of the most significant and most successful of all of the things that were launched during that period. And you get products like this. I don't want to do that. right through that period, from the first meeting to the fifth meeting, there are a whole lot of other things that went on. In 1997, there was a review of the sea level network. In 1998, there was a thermal and a salinity review in tropical moorings. In 2001, in fact, at the time of 9/11. So that was a meeting in many ways we'd like to forget, but it's still, I think, etched in Mike and my minds at least. We worked our way through that, but it was a very difficult meeting. And there are probably other things in between, to the point where we are today, where it's the TPOS 2020 project, reviewing the Tropical Pacific Observing System, and at this meeting, agreement on the Indian Ocean, and perhaps other reviews that are going to come in the future. In moving forward, in a change of chairs, Ed Harrison, who I know is watching in from afar, took over as chair between 5 and 6, and it was the time, or the birth, of the essential climate variables. I tried to look through my deep archives to find the first time that Ed or someone had mentioned essential climate variables. And as far as I can tell, it was somewhere between two meetings that were convened by the GCOS steering committee, where, in preparation for the second adequacy report. We talked about, in various documents that Ed had authored, about key parameters and essential parameters. But as far as I can tell, we didn't actually coin the term until the second adequacy report was actually published. But that change, and particularly the change in the relationship between GCOS and the UN framework for climate change, UNFCCC, was a key moment, I think, in the development of GCOS and in the development of our relationships with the satellite operators. Over the next 5 to 7 years, and I didn't have access to all of the details here, there was a lot of good work done in the panel, culminating in the Ocean OBS 2009 conference. So I asked Ed for a couple of highlights in between this and the 99 conference, and came up with this list. So the first was around vast progress at ocean satellite observing and in managing the relationship. When I looked at what was happening in 2009 compared to when I left the panel, it was really a maturing of that relationship and a maturing of the way we approached it. The willingness of the coastal and biological and biochemical communities to engage had changed. They were present at Ocean OBS 99, but we really didn't have an integrated discussion in the way that had occurred in 2009. The framework for ocean observing, which I'll show in a moment, was one of the outcomes of that meeting. There are a number of technological advances, and I think a maturing of the relationship between research and sustained observations that, again, is part of the stewardship that WOPC provides. The framework for ocean observing, I think, was again a pivotal moment in providing, if you like, a little bit of engineering architecture to the way we look at our observing system. I'm a great fan now of architecture and thinking about the way our systems operate, and Eric Lindstrom and a number of other people sat down and tried to capture this in the framework for ocean observing. And this is the diagram that I use and others use now to guide a lot of our thinking. We now have essential ocean variables, and our thinking is often now getting organised around the essential ocean variables, the requirements on those essential ocean variables, and then flowing from those requirements, the requirements on the observing system, and ultimately the requirements on the platforms that we maintain and networks that we maintain to provide the information. So I guess the question is, are we getting there? Yeah, yet. And I think in this talk I'm getting close. So I've only got 3 more slides to show. So just taking a broader view, I think when we look back, you see tremendous innovation and change over the last 30 years. It's not just because there are more dots on the map. It's because we're much more sophisticated in the way we approach both the networks and the way we use the networks and the way we manage the observing system. A lot of that has come from new technology. A lot of it has come from new knowledge. We've had some breakthroughs, but we've also had, I think, a few barriers that have, perhaps slowed our progress and not totally halted it, I don't think. The scope now is truly global and truly multidisciplinary. It is a joined-up system. It's integrated design. Keys to that are the multi-purpose, multi-use aspects. That's where we derive the sustainability and, if you like, the robustness. The diversity in technology and approaches is essential. We must have different ways of doing things. We must not put all of our effort into just one technology. High impact public goods. There are people that use the information, it's fit for purpose, and it is having an impact. We have at last, I think, learned how to treat in situ and satellite contributions as one. We've still got some ways to go, but I think we've made great progress on that. And the final point is probably the most critical. We've had good people, and we continue to have good people that work on the observing system, both in the networks, in coordination groups like the WOPC and various other fora. It's those good people, that enthusiasm, which is critical. Are we there yet? Second instalment. I think we have a long ago surpassed the goals and dreams of the WOSDP and in the early days of OWPC. We had great aspirations then. We were always trying to push the boundaries. When I look at the plans of the group that we've been discussing here in the last few days, I think they're trying to push those boundaries as equally as hard as we tried to push them back then. Looking at the challenges, some of them are very daunting, but trying to choose those which are actually doable. We have not made the progress in climate models that we envisaged in those early days, 15 to 20 years ago, but there has been great progress in areas that we weren't thinking about back in the early 1990s, such as in G'day Ocean View, in reanalysis, in some aspects of seasonal prediction. Some technologies did not make it, but many did. Some spectacularly so, I think. And you only have to look at, say, the Tropical Mooring Network and Argo as two examples of great successes relative to where we were 20 years ago. Gliders and sustained boundary monitoring, which was one of the topics of debate at the OceanOBS 99 conference, is still just out of reach, but it's getting closer. And this group here is discussing in a number of pilot projects where we might test the viability of doing that in the future. WOPC and the people that work with them, I think, have made a great difference. Its list of achievements over 20 years of work is impressive. And I think you should be all very proud of the work that's being done. Biggest risk is probably around complacency and perceptions that the observing system is self-sustaining. It is not. It requires continual work. It requires good people enthusiasm to keep it going. We should be game and willing to change and innovate. It keeps the observing system fresh, and it keeps our user community engaged. Good communication remains essential, and perhaps even more so as the scope and complexity of the observing system grows. And the final slide. So this is a bit more lighthearted, and I probably should have, kept at the bottom and the key lines down the bottom hidden. So what it's going to look like in 20 years from now. So my guess is that this panel and WOPC 40 will be spending a lot of time thinking about OceanOBS 39. I think I'm going to anticipate somewhere around 2,000 participants. I know you're looking for 1,200 this year, but my guess is 50% growth every year is perhaps what you'll get. It's going to be held in a submerged auditorium, and I think I've got a picture of your location here. So this is where you're going to be holding it. In the middle there's an auditorium which is actually submerged. They're just starting to build this in French Polynesia, or planning it now. And so that's where you're going to be holding the meeting. And it's going to be a great, fun meeting. My guess is that 3 people from this room will still be on the WOPC based on experience. We have 3 people or 2 people here that have been on pretty much since the start. I think Katie's probably going to be the co-chair by then. She'll be, she won't be 30 any longer, or 40. Yoni may still be there. He's been hanging around for a long time. It's probably going to be called the Ocean Observations Panel for Everything. I suspect there's just going to be some rationalisation and combining, and everyone will want to change its name anyway. I'm hoping that Bob Weller and Mike and myself will have retired and be enjoying life, but I don't know, Mike. We may not. We may still be hanging around. The observing system, I'm guessing by then we'll have a great glider fleet out there, maybe 450. It'll be a core contribution. I think we'll have the first ocean current measurements from space. Johnny's talking about technology that is already there to do some of that, but I think we'll have dedicated satellites to do that. They're probably going to be around 5,000 Argo floats. David, I'm optimistic. I think you'll keep that level. And a lot of those are going to be deep profiling floats back then. I didn't know how to guess how many biogeochemical floats we'd have. I think probably around 1,500. Maybe these guys will be exceed that. Sail drones and wave gliders, I think, will be just one part of the observing system. And I think we'll have driverless vehicles out there, helping to service. Bob, you won't need to do that anymore. You'll just sit at your desk and you'll drive something out there and you'll service your mooring from afar. You won't even have to get out of your pajamas. Sea level and ocean temperature, unfortunately, will still be rising. Maybe by about this stage, we might be starting to see a drop off in the acceleration. It may be steadying, but we may have to wait until 2057 to see that. Models will have improved, but we'll probably still not be meeting the need. There'll be still Bob Weller saying, Jesus, you're still off by 15 watts per square metre. Go back to the drawing board, guys. What I'm really hoping for is that we will have just conducted the first global ocean research experiment. Fellas, this is the first time you saw this acronym. FGORE, it's going to be called. And it's going to really go back and change the paradigm for the way we work. It's going to be a great experiment. You're going to start planning it in about 5 to 10 years' time, and it's just going to change the way we work again. Surge in knowledge, surge in development. Large multidisciplinary experiments are going to be back in vogue, and couple models will be used routinely for all timescales. They'll be seamless by this time. So that's enough of looking to the future. Thank you for the chance to have a little bit of a chat, and Bob's going to take all the questions. Thanks, Bob. Or Mike.
Okay, thank you very much to Bob and Neville for a trip through history and a bit of a vision for the future. So we're running a little over time, but hopefully that was a useful time spent. So we will spend a little bit more time taking questions. So while people are putting messages into the chat room, are there a couple of questions from the room? We've got a roving mic in the room. Oh, it's Ray Schmidt at the back.
Yeah, Neville, right now we're sort of piecing together our observing system, not so much for climate, though we call it a climate observing system, but for weather, really, and all sorts of other applications, coastal security, maritime safety. But sometimes the variable you need to measure for climate has to be measured at a much higher resolution and got bigger concerns about the continuity of time series than you do, say, for weather observation. Is there a way that we can imagine actually having an observing system funded to look at climate itself?
That's an interesting question. In fact, it was one that was discussed in a couple of meetings over the last year, because when you look at the climate system, what's the thing that characterises it and makes it different? It's actually the quality. It's the attention we give to the quality of the observations, making sure that they're really, we're cleaning up the data sets, all of the things to get out this very small signal which is tucked in amongst all of these other signals. And I think we are making progress in that. I think we're making more use of the first pass, if you like, through weather or ocean forecasting, and then returning again and again and adding value to those data sets. What we'd like, I think, is to have a much more seamless way of approaching that. And people within the WMO community are discussing it. We discussed it in a meeting about 12 months ago. And I think it's something we've just got to continually work on. I think we are starting to see some emergence of that. Will you have a separate climate observing system? I suspect not, just simply because of the cost. And I think you guys in the US had some experience in that with the surface network, creating something that was separate from the real-time network that served weather. And it becomes very costly to maintain this. You sometimes have, two instruments sitting at the same, or maybe four instruments sitting at the same site, and you start to see a little bit of redundancy and lack of efficiency. So the best system, I think, is to have one that does both, and it explicitly targets the signals that we want.
Great. Okay, so we've been told that the mic in the room is not working, so people are going to come up to the computer. Sabrina, do you want to come and ask your question?
Okay, I'm Sabrina, co-chair of Cliver Atlantic Regional Panel, and I wanted to ask why we were not able to go a little bit more forward with the modeling part.
I think if we could parade 8 people around here to try and answer that question, that all probably give a slightly different answer. I, in my work over the last 3 years, have been looking a lot at the tropical Pacific observing system and the progress with seasonal prediction. And one of the odd things that I've noticed is that if I went back to 1995 and the final TOGA conference that was held in Melbourne, the number of people developing models and people in the modelling community working with observations, I don't know. It was probably about a third of the room that had some connection. There was a great linkage between those, and there are a lot of people doing development. Many of those people and many of those positions, particularly in the operational agencies, this is probably going to offend some of them, are doing more an engineering task. Just keeping the cogs going in those systems requires a lot of effort. We didn't get new investment to maintain that. We took the investment that was formerly in research and plowed it into that maintenance. If you look at G'day and some of the systems that are running operationally there, lo and behold, we've done exactly the same thing. In the first 5 to 10 years, there was a lot of great research and development and innovation. You look around now at even some of the biggest systems, and you suddenly find just keeping the system going is chewing out the resources rather than putting in new resources to do that, if you like, engineering and operational task. We've taken it out of the back door of research. Why would models slow down? We just don't have the investment both in the development and I think in those big experiments where you can make the paradigm changes that we need in models. And I am absolutely convinced we need almost a paradigm change in the way we're doing it. I don't know whether Bob or maybe Michael have any other comments on that, but that's certainly my view.
Great. Okay. Well, I'll be reading from the screen, so we'll be doing some double shuffling up here. And we've got some great questions coming in on the chat. There's some big picture questions and some technical ones. So we'll start with a few big picture ones while we're on a roll. So from Eric Lindstrom to Neville, what are the major contributions to society from 20 plus years of sustained ocean observing, and can we build a better case?
I didn't even have to see Eric's name attached to that. Thank you, Eric. That's a very fine question. Again, I didn't spend a lot of time on that impact side and if you like, the benefits. But if you look, and I'll just take one little part on the ocean prediction, which is an area which I perhaps know better than some of the others. When you look at the uptake of information, say, in the Copernicus Marine Environmental Monitoring System, it is really impressive. The breadth of users that are taking out product from that system is really broad, it's deep, and there are people that really care that they get those products. And they range from forecasts to data sets to reanalyses. The reanalyses, in fact, probably are one of the most used products. If I go into the seasonal prediction, and I had a long chat with the person in charge of climate services in the Bureau of Meteorology before I came over, he was passionate about the way they use our seasonal prediction models. I dared to say that perhaps they weren't all that good in some cases, but he was passionate about how important they were for both the climate services and for their water services in the Bureau. And I'm pretty sure if I walked around the other climate services, they'd be equally passionate. They still use a lot of Mike's work from the tower moorings directly in their outlooks. And so that sort of uptake is critical. why I was having an argument with him was because I want them to be just as passionate in arguing and advocating for the observing system that supports those benefits. And so joining that loop up, Eric, I think is something we're just going to have to continue to work on.
Okay, so a question from Bruce Howe. What is the state of the evaluation process to improve the present system, and can we look at do we look at pros and cons of new technologies?
Thanks, Bruce. In fact, yeah, you probably should have logged in about half an hour or an hour ago, because that was exactly the topic we were discussing in the meeting here. I'm a great advocate for the continuous review and evaluation of the observing system, as I said in those slides. And some of this is not, if you like, routine. It's getting people with good brains and willing to step out and step away from their pet subjects and actually say, well, what are the objectives we've set ourselves? How close are we to meeting those? And be willing to look at, options for change and things we can do differently. The challenge we face is, choosing chunks of the observing system and choosing in a way that we can make sense of it. So just at this very moment, I'm involved with reviews of the Tropical Pacific Observing System, and there we're trying to evaluate all of the contributions down to the level of the networks, as well as all of the other components that make that a system, as distinct from a bunch of things which are just sitting beside each other. And so I think that is one way of doing it. Bob might want to have some comments around perhaps some of the technology and how we evaluate that in that system.
Yeah, Bruce, a lot of what we've been doing at this meeting in an OWPC is moving to a platform agnostic view, centered on the essential ocean variables and understanding that for some of the climate cycles like heat, freshwater, and carbon, we're going after some of the things like heat content, upper ocean thermal structure, things like this. But we're going at it from a platform agnostic view, but understanding the climate observing principles where new technologies come in. We have to overlap them and prove the compatibility with the old, and old technologies sunset. But we don't really have we're trying to move away from a platform focus, but opening the door for increased efficiencies and capabilities and adopting new technologies.
Right. And while you're there, Bob, I've got another question for you from Eric. And he was asking, I've got to find it now, it's scrolled off the screen, I think. Whatever happened to self-deploying moorings from volunteer ships or aircraft? In the days of WOCE, several people worked on that.
Well, Mike can help me here. I think to an extent, I've seen the pallet, the sort of built as a pallet, deployable by pushing off the ship, low profile stealth moorings for use in the tropical Pacific. So that's still, that's a technology that's come into existence. But Mike?
Yeah, I think there has been some development effort along those lines. I think the issue there is not so much the hardware. You can make a self-deploying mooring, it's the payload, particularly if you're talking about subsurface instrumentation. That's very much more difficult to do, and so I think that's where that technology is somewhat slowed, because it's very hard to put a subsurface payload on a self-deploying mooring.
Okay, great. So we're close to running about 8 minutes over. So are there any other final words from both our speakers?
I think we've had enough words.
Yeah.
All right. Okay. So thank you for everybody for joining us online. I hope you've enjoyed it as much as we have here, and we'll tune in again soon for the next webinar, and stay tuned on the website for details of that. All right. Thank you very much.